All right, so we're going to finish up chapter 10. We got to talk about a few more methods for preparing alkyl halides. Remember last time we talked about preparing alkyl halides from alkanes, which was that pretty involved radical halogenation. Okay, so now we're going to move on. How to get alkanes from alkenes. Okay, and we already know two methods of preparing alkyl halides from alkenes. All right, first of all, if we have an alkene, right, these are from last unit here, we can treat it with HX, where X is either chlorine, bromine, or iodine. And we get that halogen added to the more substituted carbon. All right, because it's a hydrogen and a halogen. This was called hydrohalogenation. Okay, the other method that we had was just using a halogen, which are diatomic, so X2. And now you're just adding a halogen, so this was a halogenation reaction. And that will add two halogens, one to either side of that double bond, right? So these are two reactions that we covered previously that will produce alkyl halides. All right, and in both of these reactions, you are breaking that double bond. You're breaking that pi bond, and you're creating two new single bonds on either side. We called these addition reactions. All right, so we know two addition reactions of alkenes to prepare alkyl halides. All right. Now we're going to talk about another one here, which is what's called allylic halogenation. Which uses this N-bromosuccinimide, which we call NBS. Okay, you don't really have to know the structure, but just in case you're curious. This thing right here, this guy's NBS. All right, so this is called a allylic halogenation. So let's get an alkene here. I'm going to use cyclohexene. Does anybody remember what the heck allylic means? All right, when we have these double bonds, we have names for these positions. The ones that are on either side of that double bond, those sp2 hybridized carbons. We call these the vinylic positions. But then those positions that are one removed from those double bonds, these are what we call the allylic positions. If you remember when we were talking about resonance, we had a lot of resonance patterns that involved that allylic position. So for example, if you had a positive charge, not on the double bond itself, but in the allylic position, this would be resonance stabilized. So that pair of electrons can jump over here. All right, so this is when this sort of terminology was first introduced in the course, was when we were talking about resonance here. Okay, so now this is allylic halogenation. So which carbons do we think are going to be halogenated? Not a trick question? The allylic ones, absolutely. All right, so what NBS does is specifically brominates. There's no chlorine analog here. But it will put a bromine on that allylic position. Notice that it does not break that double bond. All right, we still have an intact pi bond, which means that I lied to you a little bit. We wouldn't technically refer to this as an alkyl halide. This would be an alkenyl halide. All right, so when you think NBS, what you want to have tied in your mind with NBS is that word allylic. All right, so for this reaction here, our NBS, we're not going to have any mechanism that we have to know for this reaction. All right, no electron pushing arrows. But what we do have to know is that this reaction too does go through a radical intermediate. So we have to take a second to talk about radical resonance. Right? The resonance structures that are available to free radicals. So we said, let's just put this one down here because it's going to be very similar. We said that these allylic, these were allylic positive charges exhibit resonance. We are going to see something very similar for allylic radicals. All right, so if I have a double bond, and in the allylic position is a radical, I'm going to see the same sort of resonance where that radical and that double bond can swap positions. I want y'all to take a second and use those fishhook electron pushing arrows we discussed last time. See if you can't take me from A to B on this resonance structure here. We talked about those fishhook electron pushing arrows that move just one electron. How would we represent this resonance here with those fishhook arrows? So we need to draw the formation of that new double bond. As well as that free radical forming on that end carbon there. All right, and the bottom line here is that allylic radicals are stabilized through resonance. We talked about how these radicals, they're really mad, they're angry. Well, they're a little less angry if they're in the allylic position here because that radical can be stabilized through resonance. Practically, for our standpoint, what this means is we need to watch out for multiple products due to resonance. All right, for this first example, I specifically picked an alkene where you didn't have to worry about that sort of thing. All right, but now let's look at an example where we do have to worry about it. Okay, so now I have a cyclopentene here, a 4-methyl cyclopentene. All right, we're going to treat this with NBS, and we want to know what our products are. But here we're actually going to get a mixture of 2 products. So why would that be? Okay, so again, we don't really know the mechanism behind this, but we do know that this will go through a free radical intermediate here. So I have a radical on that allylic carbon. So when that radical forms on that allylic carbon, my product here from that allylic bromination is going to simply have that bromine on that allylic carbon, right? Okay. But now, what about the resonance structure for this molecule here? Everybody take a second and draw me what the other resonance contributor would be for this allylic radical. Again, we're going to have our fishhook arrows showing the movement of that double bond and that radical. All right, so my other resonance contributor here, whoops, got a little copy paste happy. Now has the double bond moved and has the free radical formed over here. So what's going to be the product from this resonance contributor? I'm going to have the bromine in position of where that radical was. So we didn't put in my lone pairs. All right, so because of that radical in that allylic position and the resonance that is available to that position, we actually get a mixture of products. One is the easy one to draw. You just put the bromine in the allylic position. But for the other one, now you have to do your resonance structure and put the bromine where the new radical is formed. So we've got a mixture of products here that we got to watch out for because of this allylic radical mechanism. Right, and again, to be clear, these were our resonance contributors. Okay, so again, this one had these two products, but this was also a symmetric alkene here. All right, so it can be, we can have worst case scenario here. Let's take, for example, excuse me, thank you. All right, so this one's going to be kind of worst case scenario here. All right, so why is that? Well, because first of all, I have two different allylic positions here. And if I put a bromine on either one of those, I'm going to get a different product. All right, so everybody take a second and give me my quote-unquote easy products here, where you just stick a bromine on those allylic positions. All right, so I got two allylic positions, so when I do my bromination here, that will put that bromine in those positions, so one on top. And one on the bottom. All right, but in addition, I also have to draw my resonance contributor for each one of these allylic radicals. All right, so take a second to draw my resonance contributor for each one of these radicals here. So, if we just look at our first allylic position here, again, we got to worry about this radical moving around because of resonance. Now I'm going to have a radical forming over here and that will lead to a different product. All right, I got to do the same thing for the other allylic position. This also can have this radical moving around. Which will then, of course, lead to yet another product here. Okay, so we would have a mixture of 4 different products for this particular alkene that we started out here, all having a bromine in the allylic position here. And the reason why we got so many products is, first of all, we got 2 distinct allylic positions in this molecule, so each one would give us a different product. But then we also got to worry about the resonance of these molecules, which will lead to a different allylic position, all of which get brominated. And that's kind of as bad as you can get, is a mixture of 4 different products here. All right, but you want to just be careful and look out for that. Again, our original molecule that we picked, we didn't have to worry about it. All of those positions would have been equivalent. We just got 1 product. We did another example, which was nice and symmetric, so we only got 2 products. But if we have this completely asymmetric beast here, we're going to get 4 different products out of it. All right, so now we have one additional method for halogenating alkenes. In addition to our hydrohalogenation and our halogenation addition reactions, we now also have this allylic halogenation reaction. All right, so let's talk about from alkynes. Again, we knew of some methods to prepare alkenes, alkyl halides from alkynes. The same reagents as we had for alkenes. We have hydrohalogenation. If we take an alkyne, we can use one equivalent of that HX. Just like before, it puts that halogen on the more substituted carbon. We can follow that up with a second addition of HX. Okay, adds that halogen to the same carbon. Okay, so again, just review from last unit. Likewise, we had a just halogenation reaction. We use one equivalent of our halogen. On either side, specifically a trans addition product. And then if we add that second equivalent, we get just a whole boatload of halogens on there. Okay, so these two reactions are both review from our discussion of alkynes. They would both be methods of preparing alkyl halides, which is again the topic that we're discussing here. And from alkynes, I don't have any new ones for you. So this is it. All right, these are the two methods that we've already discussed for preparing alkyl halides, and those are the two we got to know for alkynes. All right, but now we're going to do a functional group we haven't talked about yet. How do we get alkyl halides from alcohols? And this isn't something that we've discussed here in lecture, but we've actually done this in lab already. We've prepared alkyl halides from alcohols. All right, and how do we do that? So we have our alcohol. That'd be good, actually. And what we did was we just used a strong acid in the presence of some halide ions, right? So we could just use, when we did it in the lab with our tertiary alcohol, we used HCl, for example, right? And what we get is what we call a substitution reaction. Where that halogen substitutes that OH group. All right. So this is a method to prepare alcohols from alkyl halides. And if you remember when we did it in the lab, we did two of them. First, we did a primary alcohol, and then second, we did a tertiary alcohol. And when we did the tertiary alcohol, it took about 3 minutes, right? When we did the primary alcohol, we had to sit there and boil it in the presence of strong concentrated sulfuric acid for like over an hour. All right, so this method works great for tertiary alcohols. Fantastic, no problem at all. You can do it room temperature very easily. However, for primary and secondary alcohols, you could do it, we did it, but it required what we would consider to be very harsh conditions. Super concentrated strong acid and lots of heat. All right, so for primary and secondary alcohols, you got to use those harsh conditions. Strong acid and heat. And for some alcohols, for example, like ethanol, you would just never be able to use this method because you would never be able to get it hot enough. You would sit there and you would heat it up and it would just boil and escape before it ever reached a temperature where you could actually conduct this sort of reaction here, right? So this method will work great for tertiary alcohols. For primary and secondary alcohols, you got to force it a little bit. All right, so instead they've made some like fancy designer reagents here that we can use instead. Okay, so for primary and secondary alcohols, we have two fancy reagents that we use. Okay, again, starting with an alcohol. The first one is SOCl2. And this will accomplish that same conversion, that same substitution reaction, placing a chlorine in place of your alcohol. And this does not require those harsh conditions. This is something that you can do at room temperature in a reasonable amount of time. You just need to go ahead and purchase this fancy little designer reagent here. And if we wanted a bromide we have another sort of fancy reagent here, phosphorus tribromide, PBr3. And that'll stick a bromine on there. Okay, so just two new reagents that we have for alcohols to create alkyl halides. Okay. For this one, we don't have any mechanism that we have to worry about. There's no regioselectivity in a sense because it's not an addition reaction. You're just going to swap out that OH group for that halogen. But these reactions do have this stereospecificity. And it's a type that we haven't seen before because up until this point we've really been talking about addition reactions, not so much substitution reactions. But this is a type of stereospecificity that's going to be quite common for these substitution reactions. We'll see this a lot when we discuss various reaction mechanisms next week. This was what we call a stereochemistry inversion. All right, so what do I mean by that? Let's say that we had an alcohol that had a chiral center, and we had one specific stereoisomer of that alcohol. All right, it's been a minute, but I believe in y'all. Tell me whether we have the R or the S stereoisomer here. Remember how we got to do this. We got to label our various groups in terms of their priority. So this one's first, this one's second, this one's third, and the hydrogen in the back is fourth. So then we're going to connect our top three groups, 1 to 2, 2 to 3, 3 to 4, and it's going in the clockwise direction. So what was clockwise? R. Nice. This might be a terrible way, but I remember it because it's sort of ass backwards, because counterclockwise actually has an R in it, but it's not that one. I don't know if that's helpful to anybody, but that's how I remember it. Oh, nice. Okay, that's good.
I figured it out.
So we got an R stereoisomer here, right? So now we're going to hit it with one of these reagents here that does an inversion of our stereochemistry. And so what happens is that our wedge is going to become a dash in our product. And we're left with the S stereoisomer here. All right, but again, what we call a stereochemical inversion. We turn dashes to wedges and vice versa. All right, and For substitution reactions that are stereospecific, this is the type of stereospecificity we're going to see a lot. Remember, for addition reactions, it was like the syn or the anti-addition. That's unique to addition reactions. For substitution reactions, we're going to have this inversion that takes place here. The chlorine, the reason why you have this inversion is because this chlorine gets added to the back side here, the opposite side of where that OH group is pointing. All right, again, we don't really know the mechanism for this one, so I don't want to go too much into detail here. But we'll talk about sort of simpler reactions where we do know the mechanism, and we're going to see this same phenomenon. Okay, so for alcohols, remember we did this in the lab. For tertiary alcohols in particular, we can just use those hydrohalogens. Works great at room temperature. Okay, for primary and secondary alcohols, if it's a big alcohol and there aren't any other functional groups or any worry about using these harsh conditions, then yeah, you can do it. All right, but it's not really pretty. All right, it's pretty brutal. For primary and secondary, a better way to go about it would be to use our designer resources or reagents here, our SOCl2 and our PBr3. Those would both get substitution reactions of alcohols to create alkyl halides. Our sort of special consideration here is the stereochemical inversion that we see in these reactions, where if we start out with a specific chiral isomer, an R or an S isomer here, we're going to get an inversion of that stereochemistry when our alkyl halide is formed. Cool. All right, so the last reaction we're going to talk about for this chapter is actually not a way to prepare alkyl halides. They're just something pretty cool that they can do. And it falls under this class of reactions that we call organometallic reactions. So there are two very popular organometallic reagents that we can use. The first one's what's called a Grignard, or spelled Grignard. All right, but a Grignard reagent here. If we take an alkyl halide, and we combine it with magnesium metal, something kind of bizarre happens. All right? The magnesium will wiggle its way in between the carbon and the bromine. And this, with this MGBR business in here, this is what we call a Grignard reagent. So, first of all, everybody's chemistry brain should be exploding right now because we have a covalent bond to magnesium, to a metal here, right? Covalent bonds are exclusive between nonmetals. So how do we have this covalent bond to this metal here? It's just a bizarre fact, and these bonds are actually really important because metals, we know, don't have a very high affinity for electrons at all. They have a very low electronegativity. So that means that this guy right here in this bond is not holding on to many electrons at all. And all of those electrons in that bond are sitting on that carbon there. And what do we call something that has lots of electrons? Something that's very electron dense. Exactly. And so this thing right here, these Grignard reagents have this nucleophilic carbon. All right, so what is that doing for us? Well, if we put our Grignard with our nucleophilic carbon in the presence of an electrophile, remember those alkyl halides are nucleophilic carbons. What we will get is a nucleophile attacking an electrophile, and we form a new carbon-carbon bond. This is probably the easiest and most efficient way to form new carbon-carbon bonds in the organic chemistry lab, is using these Grignard reagents. They work great. They're easy to make. Magnesium's not expensive. All right, so if you have your alkyl halide, you can just toss in some magnesium to create your Grignard reagent, and then you can react it with any nuclear or any electrophile to create a new carbon-carbon bond. Okay, this is a reaction that we will actually do in the lab the second semester of organic chemistry here. Where these things aren't going away, these Grignards. We'll talk a lot about them next semester as well. Okay, but the whole shtick is because you have this, again, organometallic, you have this metal in your organic molecule. Those metals do a terrible job of holding on to their electrons. So all that electron density sits on that carbon atom, making it a nucleophile. And if carbon's the nucleophile, then we can get a new carbon-carbon bond in our product. All right, the other one is a Gilman reagent. All right, and this is fairly similar except for it's copper and lithium. All right, but when you prepare your Gilman reagent, and this is always looks a little weird, there's actually two of those organic chains that will bind to that metal. And only one of them ever reacts, but that's how we write our Gilman reagent, is with these carbons in parentheses with this subscript 2 outside. And these react really well with alkyl halides. The Grignards kind of do, but they're kind of better for other functional groups. Let me make this distinct here. All right, so I'm going to again be creating a new carbon-carbon bond with my organometallic reagent here. I have these 3 carbons that I'm going to attach to these 4 carbons here. Okay, I'm creating a new carbon-carbon bond. And importantly, the carbons that are going to be linked together is the one at the base of the metal in my or in my organometallic compound, right? The one that has all that electron density is now going to be connected to that electrophilic carbon in my alkyl halide. All right, so everybody take a second and see if you can't draw me the product of these reactions linking these two carbons together to create a new molecule that will have a total of 7 carbons in it. All right, so if I draw my product here, I'm going to start with my 3 it really doesn't matter which one you started with, but let's just start with these 3 carbons that I had colored in red. And on this one, I'm going to draw my new bond. The carbon on the other side of that bond must be that one I had colored orange that was at the base of my halogen. All right, so now I just got to draw in the rest of that fragment. There's this one, and that one. And so these are my 4 carbons from my alkyl halide. And again, I've created a new carbon-carbon bond. All right, we've talked about it before, sort of a strategy for reactions about counting carbons to make sure you didn't make a mistake. For these particular reactions, that's going to be super important because we're making something big and ugly on the other side, right? We're not just swapping an OH for a chlorine. It's pretty easy to see what your products are for those substitution reactions. Now we're joining 2 molecules together here, so we're going to create something big and ugly on the other side. And we want to make sure we didn't add an extra carbon or forget a carbon or something like that. So just always go back and do your tappity taps to count your carbons. All right, so let's just practice this here. We're going to do kind of an easy one and then a more difficult one. Since the Gilman is the reagent, typically that would appear above the arrow if it was written in that format. Okay, so take a minute and give me my product of this reaction. Let's do. Alright, so before I get started, I just want to sort of go through and note that I have 1, 2, 3 carbons in my alkyl halide and 2 carbons in my organometallic compound. So at the end of the day, I better get 5 carbons in my product. Alright, and then I'm going to color in, just so I'm not going to make a mistake here, that this carbon right here at the base of my halogen is going to be linked to this carbon right here at the base of my metal. Okay, so let's just say explicitly here that our new carbon-carbon bond is between the carbon at the base of the halogen, which I colored in red, and the carbon at the base of my metal, at the base of the copper. I guess I could say bonded to, that'd be a more normal chemistry way to say it. Which I colored in orange. Alright, so that's the 2 that I'm going to connect. So I'm going to start by drawing my 3 carbons from my halogen. That's these 1, 2, 3. I'm going to connect a new carbon to this one. Alright, that means that on the other side there, that's got to be my orange carbon. So boom, that's my new 1, 2, for a total of 5 carbons. All right, one of the things about Gilman's that are quite powerful is that there really are no restrictions behind the functional groups that you can have on your alkyl halides. So this benzene ring right here, we'll learn next week that these sp2 hybridized carbons are a pain in the butt to substitute on. They don't work for most substitution reactions. For Gilman reagents, that's not the case. You can easily swap off and substitute on a sp2 hybridized carbon. So again, and this is pretty easy. I should have a benzene ring in my product here. Again, I'm going to connect it to that carbon. Okay. I'm going to, to those 6 carbons, I'm going to add 1, 2, 3, 4, 5 new ones. Right? And I'm going to connect this carbon here. So I'm going to start by drawing my benzene ring to this carbon here. I'm going to draw a new carbon-carbon bond. On the other side of that has to be that orange carbon that was bound to my copper. So now I can just add on. So that's 1. So now I need 2, 3, 4, 2, 3, 4, plus that branch point for a total of 5. All right, so again, these Gilman reagents are pretty powerful because we can create these new carbon-carbon bonds that also makes them kind of a pain in the butt because the product you get on the other side is this big ugly thing because you're linking your your substrate and your reagent together to form that new bond. Okay, and importantly, it is the carbon that is bonded to that copper that has that new carbon-carbon bond. Right, so my methyl group has to be all the way over here, not over here. Right, they're linked up in a specific way. Okay, the other thing that we're going to note about these Gilman reagents is that they preserve alkene stereochemistry. So stereospecificity, kind of a pain in the butt. In this case, it's like best case scenario, it's just going to be the same. So what do I mean by that? I mean, let's take our alkene here. All right, an alkenyl halide specifically. And if we treat this with our Gilman reagent, we're again going to get a new carbon-carbon bond. We're going to link these 1, 2, 3 carbons specifically at the carbon that's bonded to that halogen. We're going to link it to these 2 carbons right here, specifically at the carbon that's bounded to the metal. All right, but when this new bond is formed, it's formed in such a way that it preserves that stereochemistry. So pointed in the same direction as the bond. All right, so this bond here and this bond here is in the same direction as the old bond. All right, so the stereochemistry of that alkene is preserved. I didn't swap anything or flip those groups. I don't get a mixture of products. I just get the same direction. My new bond is just in the same direction as where my old bond was. All right, so then let's just finish this off by summarizing. Okay, I think what should I do? Okay. Okay, so first, let's just practice probably what is the biggest pain in the butt reaction we learned today, those NBS reactions. So give me the product. Let me make this smaller. So just practice by drawing the product of these reactions here. broke my notes app. Hold on. We are not doing redox here. There we go. All right, so remember NBS, when you think NBS, you think the allylic position, right? So one carbon removed from that double bond. Okay, and so when the radical forms in that allylic position, I'm going to get my bromine added there. Okay, what about the other allylic position? Would this have given me a distinct product? No, so in this case I don't have to worry about that, but I do still have to worry about the resonance of this allylic radical. It's going to come down here, break that double bond, and so I'm also going to see my radical forming over here. And that will lead me to a distinct product because that bromine is now going to form where that radical was, right? So this would be the mixture of products that I would get here. All right, and again, we got to worry about this mixture of products because we have this resonance for our allylic radical. All right, it's going to move due to resonance. Okay, so now these Gilman reagent reactions here, I'm going to be connecting these 1, 2, 3, 4 carbons, specifically at the carbon bonded to the halogen, to these 1, 2, 3, 4 carbons, specifically creating a new bond with that carbon bound to my metal. All right, so I'm going to start by drawing my 4 carbons. Again, my new bond is going to be to the carbon that was bound to the halogen. All right, but then when I form this new carbon-carbon bond, I have to preserve the stereochemistry of my alkene, so that new bond has to be pointed up, just like the old bond was. All right, and then who lives on the other side of that bond? It has to be that carbon that was bound to the copper. All right, so that's that one there, so then I just need to draw in the remaining 1, 2, 3, giving me my total of 1, 2, 3, 4 carbons that I created. And so in addition to these two, these were kind of the biggest pain in the butts of the reactions that we covered today. The other ones that we covered was how to create alkyl halides from alcohols. If you start out with a tertiary alcohol, you can just use the hydrohalogens just like we did in lab. But if we have a primary or a secondary alcohol, we want to use one of these fancy reagents here, the SOCl2 or the PBr3. Those will also substitute out OH groups for halogens. The only special consideration we have to make with these particular reagents is that there is a stereospecificity. In particular, we see a stereochemical inversion when that new bond is created. So if your OH group was on a wedge, your new bond is going to be on a dash, and vice versa. If your OH group is on a dash, your new bond is going to be on a wedge. Cool. All right, that does it for chapter 10 here. One more to go.